Chem Tech Laboratory tutorial. Today we'll be looking at hybridization. Hybridization is the mixing of two atomic orbitals to give two molecular orbitals. And this mixing means each of the orbitals of different energy will come together to form a different shape and appear in the same energy. We have several types of hybridization. We have the Sp3 hybridization, Sp2, Sp, Sp2d, Sp3d, but today we'll be looking at Sp2, Sp hybridization. While we're looking at hybridization, we know that carbon has this uniqueness as it can form a bond within itself and with other elements. This carbon has the ability to form longer chains of itself. The characteristics of carbon having to form longer chains of itself is because it has a tetravalent ability. Now, the ground state of carbon is 1s2, 2s2, and 2p2 because the atomic number of carbon is 6. Now, carbon will now hybridize itself as 1s2, 2x1, then the p orbital has 3 subshells, which is px, py, and pz. Now, the Hooke's rule states that electrons are singly filled before pairing. Because of Hooke's law, one of the electrons at the s orbital will transport itself to occupy the p orbital as electrons are singly filled before pairing. So, the configuration of carbon becomes 1s2, 2x1, 2px1, 2py1, 2pz1. So, this enables carbon to exhibit catenation, that is, for it to form longer chains of itself. Now, if carbon uses s orbital, one of the s orbital, to form bonding, if you form bonding with this and this, we'll call it sp hybridization. If you form bonding with x, one of the p, x, p, y, it becomes sp2 because it uses p orbitals, ps and py. Now, if it forms bond with 1s, one with px, py, and pz, it becomes sp3. Okay, now we are going to give an example of an sp3 hybridized compound. Example is methane. Methane. Note that all single bonds of carbon, where carbon uses all its orbital, is called sp3 hybridization. Now, carbon, we know that carbon is 1s2, 2x1, 2px1, 2py1, and 2pz1. And this carbon needs to bond with 4 hydrogen. Hydrogen is 1x1, and we have 4 hydrogen there. So we have 4 hydrogen, so it becomes 1x1, 1x1, 1x1. So one of the s we bond with this. There is the first hydrogen. The second hydrogen we bond with the p, 2ps of carbon. The third hydrogen we bond with the 2py of carbon. And the last hydrogen we bond with the 2pz of carbon. And therefore, it becomes C to H So this becomes an Sp3 hybridization. The orbital representation will now be, and the x orbital is spherical in shape, and the p orbital is globular in shape. Now, what are these bonds? We call this bond sigma bond. Why is this sigma bond? Because it's an edge to edge of x orbital of hydrogen, x orbital of carbon. Edge to edge, s orbital of hydrogen, p orbital of carbon. Same applied to the third hydrogen and the fourth hydrogen. So, if we want to draw it, we would bring carbon. Carbon is spherical, x. Then the hydrogen is spherical, which is also what? X. That is edge to edge. Carbon, hydrogen. Now for the p orbital of carbon, p orbital of carbon is p orbital of carbon. Then p orbital of carbon, the second p orbital, and the last p orbital. Then the x of hydrogen, the x of hydrogen, the x of hydrogen. So this is the head to head. So when you represent this, that is px, x of hydrogen, one x of hydrogen, carbon, py, one s of hydrogen, and pz, one s of what? Hydrogen. So when you view this, the shape becomes something like this. And we are saying that this angle is 109.5 degrees. So it forms a tetrahedral shape. So all Sp3 hybridized compounds are what? Tetrahedral in shape with a bond angle of 109.50. And that is that for Sp3 hybridization. Thank you. Sp2 hybridization. Welcome to Chemtech Laboratory Tutorial. Today we'll be looking at Sp2 hybridization. Example of an Sp2 hybridized compound is C2H4, which is the alkenes, from the family of alkenes. They are all what? Sp2 hybridization compound. Now, how do we illustrate that? In alkenes, in ethene, this alkene is called ethene. In ethene, we have two carbon, and we have 4 hydrogen. How is this bonded? One carbon we know has its hybridized orbital to be what? 1s2, 2x1, 2px1, 2py1, and 2pz1. Then the second carbon, carbon 2, will be 1s2, 2x1, 2px1, 2py1, and 2pz1. So this is the hybridized configuration of carbon. Now, what about hydrogen? We already know that hydrogen is 4. So stating that one hydrogen is 1s1, the second hydrogen is 1s1, the third hydrogen is 1s1, and the fourth hydrogen is 1s1. In this hybridization, the two carbon will first combine, will first overlap themselves to form a bond. And what do they use in overlapping? Like I told you, I said end-to-end overlap of orbitals XS is a sigma bond. Then these two will first overlap. And when they overlap, this is how the structure will be, C to C. What is the C? We are using the end of carbon to the end of the other words, carbon to overlap. Now, when the carbons have overlapped, hydrogen will start forming bond with each of the carbon atom. The first hydrogen will form a bond with px of the first carbon, 1x1, px1. The two of them will combine to give x, end of x, and the doorbell of p, orbital of carbon. So this is s of hydrogen, and this is px of carbon 1. Then the second hydrogen will form a bond with the second px. You see, so it's edge to edge of the second carbon. So this is how the structure will be. You see, the spherical structure of hydrogen is bonded to the doorbell shape of carbon 2, px. They form the bond, edge to edge. Then, same applied to the third hydrogen, we bond with the first carbon of py, and the fourth hydrogen we bond with the second carbon of py. So the same shape will be given to us. Now we will now have this one bonds with this, and this bonds with what? This. Then we will have 2pz1 of the first carbon remaining, not used for bonding. We have 2pz1 of the second carbon remaining, not used for bonding. So let us bring the structure together. This is the spherical of the first carbon. This is 2x1 of the first carbon. Then the 2x1 of the second carbon. So when these two come together with end to end, they form a bond. Now, it means carbon has used its 2x to form a bond. What is left in carbon is 2px1, that's for the first carbon, 2py1, 2pz1, 2px1, 2py1, 2pz1 for the second carbon. And we are saying that in 18 there are 4 molecules of hydrogen. So the 4 hydrogen is exhibiting 1x1, 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 1x1. The first hydrogen we combine with its s orbital to the p orbital of the first carbon. So we want to show it here. Sp3 hybridization, like I said, that there is an end-to-end overlap of this the first carbon and the second carbon. That is the first thing that occurs. So this is the spherical shape of the first carbon, C1, 2x1, combining with the second carbon, spherical shape, which is what? 2 carbon, 2x1. So we are combining. Now the p orbital will pick up what? The 2px1 of one of the carbon. 2px1 will form an overlap with 1x1 of hydrogen, and we will have something like this. The first carbon, px1 will take one part of it to form the spherical of what? 1s1 of hydrogen. Then the second hydrogen will combine with the 2p-Y1 of the first carbon. Remember that the first carbon is this. So we take the second hydrogen, the orbital p. So let's assume this is the X overlap. There is 2p-Y1 and 1x1 of hydrogen that's combined. Then the second one hydrogen will combine with the second 2ps of the carbon. You put, you know, p orbital is double, so x. Then the spherical of what? The 1x1 of hydrogen. Same thing applies to this because the second p will bond Y of carbon will bond with what? The 1x1 of what? Hydrogen. So all the hydrogen have been bonded with each carbon. 2 hydrogen to 1 carbon, 2 hydrogen to another carbon. So this 2pz1 of the first carbon, 2pz1 of the second carbon were not used for bonding. So because they were not used for bonding, they will come here to overlap. Let's draw the diagram of the s orbital, of the p orbital, 2pz. Then the diagram of the p orbital of the second one, 2pz. So they were not used for bonding. So you are seeing the complete loss. And because they are not used for bonding, they will just form, they will just combine by lateral, by side to what? Side, to form a pi bond. So the formation of pi bond is formed by side to side of what? P orbitals. So if you view this, it will be something like this. Carbon, carbon, the bond of this, which is this. Then the ones not used for bonding, that is, which forms the pi bond. So here becomes the pi bond, here becomes sigma bond. Then that of one hydrogen, one hydrogen, one hydrogen, and the other hydrogen. So this becomes the shape of an sp2. So this angle here is 120 degrees. So it has an angle of 120 degrees. It has two bonds, one not used for bonding and the other one used for bonding. So it have an angle of 120 degrees. So an angle of 120 degrees will give us a triangular planar. That means it's triangular. So it's something like this. Triangular. So the shape becomes triangular. Every shape of sp2 is triangular planar. Planar because we have a pi bond that we are not used for bonding. Thank you for watching, and please keep on liking, subscribing to our channel.